Good morning, friends. We'll be discussing about the electric machines, the subject called the electric machines, which will be very much useful for your almost all the competitive examinations related in the engineering stream. So, whatever exam you are writing in engineering perspective, like GATE or the PSC or UPSC examinations, so any other competitive examinations, electrical machines is a very important subject, and this subject itself is a very basic functioning of electrical engineering, like the machines working, how a generator is working, how a motor is a torque is produced inside a motor, how the energy conversion is happening, what is armature reaction, how it is reduced. All these things are very basic things as a electrical engineer should know. So we'll be discussing the electric machines, and we'll be dividing the class like this. First, we'll move on to the uh, DC machines. We'll be discussing about the DC machines. Then we'll move on to the AC machines. We'll start with transformers, and then we'll move on to induction machines. Then we'll move on to synchronous machine. And we'll move on to a special types of electrical machines like single phase machines, reluctance motor, like that. So we'll be organizing the class like this. Almost 3 to 4 hours will be required for covering each area. So we'll be starting with DC machines today. DC machines. As we all know, the term machine, what it means. A machine is an equipment which is capable to convert one form of energy one form of energy to another form of energy. As we know that electricity or electrical is a type of energy, which is, as we know, this is very useful and it is very convenient to transform to one form of energy to electrical energy, and vice versa. Electrical energy can be converted back to any other type of energy very easily. That is why we are getting the electrical energy as most of the popularity. Okay. So if a machine is converting a mechanical energy to electrical energy, then that type of machines are known as generators, right? If you're using some shaft or some high turbines to rotate the high inertia mass, and this rotational energy or this kinetic energy will be converted to electrical energy, right? That is what is happening inside a generator. Inside a generator, we'll have a huge shaft where the mechanical energy is connected, or a high potential energy will be kept in the higher height for the hydroelectricity. So this water will be coming down, and this kinetic energy will be converted to rotate this turbine shaft mechanism. So once this shaft is rotated, either using the turbine mechanism or by the steam engines, any other mechanism, you are trying to rotate this shaft. So by this rotation, this kinetic energy or this associated mechanical energy will be converted to electrical energy. So those type of machines are called generators. And vice versa, if electrical energy, if it is converted to mechanical energy, those type of machines are called motors, right? You know this. So a machine which is operating in DC means direct current, those type of machines are called DC machines. A machine which can be either a motor or a generator, which can operate in direct current, is called as DC machine. As simple as that. So today we'll be discussing the constructional features of the DC machines and the EMF generation. Most of these things will be covered today. So coming to the construction of a DC machine. I'll start with rotor circuit to draw it easily. If this is my shaft, and there will be windings over this shaft inside the slots in the rotor circuit, and above that you will have an air gap where nothing will be there, and above that you will have some poles whose shape is like this. I am drawing a 4-pole machine. That means two pole pairs will be there. One pole pair will consist of a north pole as well as a south pole. So consider this as north pole, and this will be south pole, this will be north pole, this will be south. So alternatingly, these poles are named. And this is connected like this to provide some mechanical support. And all these things will be covered. So this. So this is the basic structure of a DC machine. We'll discuss one by one. So first thing, we'll start with the stator side. So the rotating mass is called rotor, and the stationary side of this machine is called stator side. So in the stator side, the outer covering of this machine is called yoke. So the first thing we are discussing will be yoke. So the main purpose of this yoke is to provide a mechanical support to the entire machine. So a mechanical support will be provided using this yoke. And one more purpose is uh, there. If you know about these poles, if you have some poles like this, if you have a north pole here and a south pole here, we know that the magnetic flux will be always flowing from north pole to south pole, right? We know that the magnetic flux will be flowing from north pole to south pole. So inside this rotor circuit, from this pole shoe of this north pole, fluxes will be coming to south pole like this, right? Right. So if you have a north pole, as we know that you cannot make a north pole alone. So once you're making a north pole, the opposite side of that magnet will be obviously south pole. So the opposite side of this magnet will be south pole. The other side of this magnet will be north pole. So these fluxes coming from north pole to south pole will be again circulated back like this. Here also the fluxes will be coming from north pole to, and it will be ending in the south pole in this direction. Right. So if you have a south pole here, obviously you will have a north pole here. So the fluxes coming from this north pole will be communicated or the flowing through the south pole through this yoke. Back fluxes coming from this backside of this north pole will be coming to the north pole of the other poles through yoke. So this yoke is providing a path for the flux. Okay, is providing a path for the pole fluxes, pole flux. Now the question is, how much flux will be flowing through this yoke? How much flux will be flowing through the yoke? Suppose the flux per pole is 5. If flux per pole is 5, then the total flux flowing through one segment of one segment of yoke will be, say this is the flux, the complete flux per pole. If it is 5, the opposite side also this 5 will be coming, right? Say this north pole, this part of north pole will have flux per pole which is 5. So one half of this flux will be flowing towards left hand side, and one half of the flux will be flowing through the right hand side. So the total flux is splitted into two parts, one towards left side, one towards right side. So the total flux flowing through one segment of the yoke will be always 5 by 2, one half of the total flux. So if the flux per pole is 5, then the flux flowing through the one part of the yoke will be 5 by 2. Right. And coming to the construction of this yoke, this will be cast iron, mostly used for the small type of machines. And fabricated steel will be used for large machines. The next part of the DC machine is field poles. Field poles. You see this? This is a pole. This part is called pole, field pole. And this is pole shoe, and this is pole core. This part is called pole shoe. This part is called pole core. Right. So if you have a pole like this, this entire part is called field poles, field poles, and this face is called pole face, and this part of this pole is called pole shoe, and this part is called pole core. Right. So field poles will have pole core plus pole shoe, and it is normally made from cast steel. And make sure that the pole shoe is laminated. The pole shoe is laminated to reduce the eddy currents flowing through the pole shoes. So what's the purpose of this pole shoe? What is the purpose of this pole shoe? If you want to make this as a north pole, what you have to do? The fluxes should be coming outwards, right? If you need to make this pole as north pole, the fluxes should be coming out. So you have to, basically we are talking about the electromagnets, not the permanent magnets. Permanent magnets will not be used for high rated machines. Okay, so permanent magnet machines are there, but normally for a higher rated machines, the permanent magnets cost will be very high. So we'll be using only the electromagnets. So we'll be providing a winding over this pole core so that this pole shoe will act as a north pole or south pole. So in order to make this as north pole, in which direction you need to wind the windings? We know that this direction, the cross sign indicates that the current is flowing inwards. And if this sign, dot sign, indicates that the current is flowing outwards. Right. So in which way you need to wind the field windings over the pole core. We know that right hand rule, right? If the current is flowing, right hand thumb rule, if your thumb is showing the direction of the current, if you hold your fingers, the fingers direction will show your magnetic field around that conductor, right? I repeat, if you hold your right hand in the direction, the thumb direction showing the current direction, and you are holding your fingers, if you're holding your fingers, the fingers direction will show the magnetic field, right? Or vice versa. If your thumb shows the direction of the flux, then your fingers, holding fingers, will show the direction of the current. Okay. So if you need to provide a flux like this, if you need to provide a flux like this, means you are interested to make a north pole, so that the fluxes should coming out of this pole through. So hold your right hand thumb towards right, okay, outwards the north pole, and hold your fingers, all your fingers. This fingers direction is showing the direction of the current. So in the upward side, in the upside, your fingers or the current will be coming out of this plane. Right? So out of this plane means shows that it is dot signs, and here it is going inside. Right. So obviously, if you need to make a field poles, you should have field windings. These windings are also known as exciting windings. And the current you are applying to this field winding should be DC. Right? If you are giving a current, yeah, this dot sign shows it is current is going outwards, and cross sign shows the current is going inside. That means this current is continuously flowing around this pole core. Okay, so suddenly if you are changing the direction of this current, suppose the current is flowing in one direction, after a few seconds you are changing the direction of this current, what will happen? This north pole will act as south pole, right? Instead, if you are using AC, okay, instead of using DC, you are directly giving it as AC. That means the 50 hertz AC signal means in 1 second the sign is changing positive to negative 50 times. Right. In that case, what will happen? This pole will act as north pole for few milliseconds, and after 20 milliseconds it will act as a south pole, and again after 20 milliseconds it will act as a north pole. So it is continuously changing. Right. That means you cannot use an AC current for excitation purpose. So you should use only DC currents for excitation. The case is valid for all the machines, not only for the DC machine, for AC synchronous machine, alternators, everywhere it is applicable. Right. Now we have a term which is called interpoles. Interpoles. These interpoles are located in between the main poles. Interpoles are located in between the main poles. So these are interpoles. That means these interpoles are located between the main poles of DC machine. And the shape of this interpole is tapered. It is not perfectly rectangular. It is tapered at the root to avoid magnetic saturation. And the main purpose of this interpoles is to reduce armature reaction. Armature reaction is a term, or it's an unwanted phenomenon which is weakening or distorting the main field flux due to the current flowing through the armature windings. We'll be discussing in detail in the later classes. So it is a bad phenomenon. It is not. It is an unwanted phenomenon in DC machine. Not only in DC machine, in almost all the machines we have armature reaction problem. So the main effect of this armature reaction is it will reduce or distort the main field flux. Okay, due to the current flowing through the armature windings. So if you are providing interpoles, it will reduce this effect of this armature reaction. We'll be discussing in details in the next class. And another function of this interpoles is for better commutation. What is commutation? The process of converting AC to DC is called commutation, or vice versa. The process of converting DC to AC is called commutation. That means basically all the machines are working in Faraday's laws, right? So if you are rotating a current carrying conductor, or if you are rotating a conductor inside a magnetic field, this magnetic field will be continuously cut using these conductors. So a EMF will be induced inside this conductors. Okay. What is the nature of this EMF, or what we call the direction of this EMF? Using Lenz's law, we can show that the direction of this induced EMF will be in the opposite to reduce the cost of producing that. Right. So basically, it will be an AC, alternating in nature. Since this is rotating, this field winding is rotating between this, not field winding, sorry, the armature windings are rotating in between the field windings. So this induced EMF as well as the induced current will be AC in nature. But we know that we are discussing about DC machines, right? So we need to get a DC current at the outwards. So this produced induced EMF alternating AC induced EMF should be converted to DC before coming out of this machine. This process of converting AC to DC is called commutation. This will be discussed in detail in the next class. Another important winding inside the stator is compensating winding. Compensating winding. These windings are also placed inside the slots. These windings are placed inside the slots in the pole faces. Pole faces. Remember the pole face inside the North Pole and South Pole. You have a pole face, right? Inside that pole face, there will be some slots. So this compensating winding will be winded along this slot in the pole faces. This winding is analogous to, can anyone guess this? This winding is analogous to damper windings in alternators. We'll be discussing all these things in the coming classes. So these compensating windings are just windings which are kept inside the slots in the pole faces. Okay, these are only used for very large machines. It's not seen in very small machines. The main purpose of this compensating winding is to reduce armature reaction and to improve the commutation. Yeah. So both interpoles as well as compensating windings can reduce the armature reaction as well as it can improve the commutations. So make sure that this compensating winding is only used for large machines because it is highly complicated to construct these windings inside these pole shoes. So these are mainly significant only for the very large machines. And obviously you will be having some brushes, right? There will be some brushes where this AC currents will be coming outside. The AC current is produced inside the armature, which is placed inside the rotor. So this rotor segment is connected to the stator. We have to take the connections outwards, right? So the part of the stator which is connected to the rotor circuit is called brushes. It's basically the connection from commutator segments commutator segments which is located at the stator, and it is connected to the armature windings, right? And make sure that your brushes are made up of carbon. It is not much costlier, and it is very useful in the process of commutation. So these carbon brushes are normally used for almost all machines, not only in DC machines, but if you're using some connections in induction machines where we are using the slip rings, the part of the machine which is continuously in contact with the stator as well as rotor will be the carbon brushes. Make sure that these carbon brushes are located at the stator and it is stationary, and the rotor segments or the commutator segments which is located in the rotor, which will be continuously in contact with the brushes. Next is coming to the armature segments. We have armature winding, which is the main part of the machine. Armature winding. These windings are made up of copper. Made of copper windings. This will have numbers of coils, and each coils having one or more turns. And we have two types of windings, as we know that one is lap winding and other is wave winding. Lap, lap windings are normally used for high current applications. High current applications. And wave windings are used for low current applications. These armature windings will be winded over armature core. This armature winding will be winded over the armature core. It is the housing of armature coils in slots. It also provides low reluctance path for the magnetic fluxes. Right. And it should be made up of thick laminations of silicon steel or any other magnetic material to reduce eddy currents. Right. And the last part of this machine is the commutator. Make sure that this commutator is part of rotor. It's part of rotor, not in the not in situated in the stator. In stator, we have brushes where these brushes will be in contact with this commutator segments, which is located in the rotor. So all the commutator segments will be rotating and the brushes will be in the stationary. So these commutator segments will have in continuous contact with these brushes. That is why we are seeing some small sparks. There will be some small spark right inside this AC to DC conversion where this commutator segments are there. And we know that some of you might have noticed the location of these brushes. The location of these brushes should be exactly where it should be, magnetic neutral axis, right? If it is not located at the magnetic neutral axis, there will be a high spark happening when a commutator segment will be in the contact with the brushes. All these things will be discussed in the next class. So we have a commutator which is located in the rotor circuit. It is made from copper. And the main purpose of this commutator is it converts AC to DC and DC to AC. For generators, the induced EMF will be converted to outwards direct current DC. So this is the case for generator. And for motors, motor we are giving the electric energy, right? We are giving DC input to the armature, and this DC cannot be directly taken inside this machine. Since it is a rotating machine, it have to be converted to AC. So the input DC is converted to output, or the armature AC for motor. So the main purpose of this commutator is converts AC to DC. What is shaft? Obviously, a rotor will be associated with a shaft. This shaft will have a very high inertia, and it will be connected to mechanical systems. Mechanical systems. Right. So this shaft will be connected to mechanical systems, where in the case of generators, this mechanical system will be a turbine governor system, where a high mass of turbine will be connected, and this turbine will be continuously rotating due to some external forces like high hydropower plants, the high water plants coming from the very high height, which will be falling towards the blade of these turbines, which will cause this turbine to rotate, or some steam turbines. A steam will be continuously produced, and the blades will start to rotate in the direction of this steam application. So basically, this shaft is connected to the mechanical system where the mechanical energy is applied. So basically, this mechanical energy will be converted back to electrical energy in case of the generator, and this electrical energy input will be converted to output mechanical energy in the case of motors. Okay. I hope up to this you are clear. So in this class, we have discussed about the basic construction features of the DC machine. In the next class, we'll be discussing about the armature reaction and the commutations in the DC machine. Okay. Thank you.